So last time we have seen an example of overflow. We have looked at the range of signed numbers, 2's complement numbers. So let's start and look at the overflow issue. So in this example, so we see a 4-bit number representation in 2's complement. Okay, so these are the all possible numbers. So I can start from +7, which is the maximum, and then I can represent all the numbers down to the -8, right? So any other number I cannot represent in this representation, right, using 4 bits. So if I need to represent more bits, I need to increase my bit width, right? Instead of 4, I need to add some more bits so that I can represent larger numbers, right? So the issue, what happens here, if we do an arithmetic operation, if I need to represent +9, actually this is like a circle representation. I will be going to the other side. So instead of +9, I will be representing -7. So let's say if I am adding +7 and +2, so theoretically I should get +9, right? But since I don't have enough bits to represent, this is what's happening. So +7, so this is like +8 and this is like +9. But so what it is giving me, the addition will give me this 1001. So in 2's complement, this is actually -7. So I was expecting to get +9, but the addition is giving me -7. So we can verify this. So in binary, this is +7 and this is +2, right? If I add this, this is 1 and 1, 0, 1, 0, 1. So this is what I got, and from the sign I know this is a negative number, right? So I will teach you a short way of finding the magnitude of this number. So I will say the weight for this is -8 and this is +1. Okay, so if I add them, -8 + 1, so I will get -7. So this number is -7. So this is a short way of finding out the number in 2's complement for the negative numbers. Let's do another example. So if I give you 101101, so this is in 2's complement. If I want to find the representation in the decimal, so I will know this is a negative number. So the weights are here 1, 2, 4, 8 and 16, right? Okay, so then I will take -16 for this position. Then I will have +8, +4 and +1. So what is this number? This is -3 in 2's complement. Okay, so this is how you can find the negative numbers representation in decimal using 2's complement. So this is a short way. And one more thing, I would like to teach you how to take the 2's complement. So let's say 101101. So if I would like to take 2's complement of this number, what can I do? The long way is you invert all the bits, right? And then you add 1 to it, right? This is how you do it. So this is the long way. Let's do it with a short way. So in this case, what we do, we start from the right and we go until we find the first one. So this is our first one. I keep the first one and then I invert the remaining. So this is keep the first one and invert the rest. Okay, so then the first one is in the first bit position and then I invert the remaining one, 1 0 0 1 0. So this is the faster way of, or shorter. Okay, as you see, both are equal. Okay, so this is a short way of taking a 2's complement. Sometimes it might be useful to you. So let's do another example. If I give you 0 1 1 0 1 1 0 0. So this is a 8-bit number and I want you to take 2's complement. So I start from the right and I go until I find the first one. So this is my first one. So I keep 0 0 1 and then I invert the remaining. So I invert these bits on. Okay, 0 1 0 0 1. Okay, so taking a 2's complement or taking a 1's complement means we are negating a number. So what is this number in decimal? Okay, this is 4, 8, 32 and 64, right? So this is plus 108. If then this number is minus 108 in decimal. Okay, so let's find what is this number. So this is minus 32, and we have plus 8, plus 4, and plus 1. So what is this? This is minus 19, right? So this number is minus 19. If I take the 2's complement, I should get plus 19. So this should be plus 19. So let's check it. This is 16, this is 2, this is 1. So if you add all of them, then you got plus 19. So taking 2's complement is similar to negative. Okay, so then let's do some more examples with the overflow. So let's do some addition and then see the overflow. So we have, let's say, 4 bits, and then I will be adding plus 7 and plus 4, right? So we expect this should be plus 11, but because I cannot represent plus 11, there will be an overflow, right? So this is 0, 1, 1, 1 in 2's complement. This is 0, 1, 0, 0. So if I add them, I will get 1, 0, 1, 1. Okay, so this is minus 8. So this is plus 2, this is plus 1. So if I add this, so what is actually it is giving me is minus 5. So there is an overflow, right? So let's do another example, and then we take two negative numbers. So let's say I take minus 3 and minus 6. So if I add these two, I should get minus 9, right? So what is minus 3? So this is minus 8, and I need 5, 1, 0, 1. So this is minus 3. So to get minus 6, so this is minus 8, and I need to add plus 2. So this is plus 2. So now I need to add that 1, 0, 1, 1, 1, 1, 1, 0, and I have a carry of 1. But since I have only 4 bits, I need to discard this. So if I look at this, what is this? This is plus 7. So it means I got an overflow. So how do I know it's an overflow? Because I am adding two negative numbers, but I am getting a positive numbers. And at the above example, I am adding two positive numbers, but I am getting a negative number. That's how I know there is an overflow. So what is the condition for the overflow? We can write if I add two positive number and the result is a negative number. So this is one condition for the overflow. And what is the another condition? If I add two negative numbers and the result is a positive number. So this is the condition for the overflow. So later on we will be writing the Boolean function for this overflow condition. So for example, if my numbers are A and B, so the overflow can be written like this. If A is bigger than 0 and B is bigger than 0 and my sum is C is A plus B and C is less than 0, or the other condition is A is less than 0 and B is less than 0 and C is bigger than 0. So if one of these conditions is satisfied, we can say there is an overflow. Why overflow is important? Because if there's an overflow, our addition is wrong, right? Whatever the operation we are doing, it is wrong. So let's do another example. And in this case, let's add plus 15 and minus 6. And assume we have 6 bits. So this is plus 9. Right, so what is the range for the 6 bit? The lowest negative number that I can represent, it is minus 2 to the 5. So this is minus 32. And the maximum number I can represent is 2 to the 5 minus 1, which is plus 31. So since we have 6 bits, there should be no overflow, right? We can easily do this addition. So if you do this, it is 0, 0, 1, 1, 1, 1. This is plus 15 and this is minus 32 and I need minus 6, right? So I need to add plus 26. So this is 16, 24 and 26. So this is plus 26. So this should give us minus 6. So this is plus 15. Right, so if I add these two, so what will we be getting? 1, 0, 1, 0, 1, 1. So this is 1, 0, 1, 0, 1. So since we have these 6 bits, we cannot take this. So when you look at this, we will be getting plus 9 here, and there is no overflow. In this example, what we did, we added a positive number with a negative number, right? So overflow never happens if you add two numbers with different signs. Okay, so there is no way an overflow to occur if you add two numbers with different signs or opposite signs. Okay, so this is one thing. So overflow only occurs if you add two numbers with the same sign, either positive positive or negative and negative. Right, we can also do some subtraction, right? Let's do some subtraction with 2's complement. So let's say I will be doing 9 minus 6, right? So then I can say this is plus 9 plus minus 6, right? So actually doing a subtraction is in 2's complement. You can also do it with the addition, right? So what is plus 9? Let's use 5 bits. Use 5 bits, and we will be doing it in 2's complement. Right? What is plus 9? It is 1, 0, 0, 1. So this is 9, but we have using 5 bits. So this is positive 9. And what is minus 6? So I have 5 bit positions, right? So since this is a negative, I have a 1 here. Weight here is minus 16. So to get minus 6, I need to have 10 here, 1 and 1 here. So this is minus 6. So I will be adding 1, 1, 0, 1, 0 here. So we add these two, 1, 1, 0, 0, 0, 1. And we discard this because we are only using 5 bits, right? So what is this number? This is plus 3 in decimal, right? And the result is correct. It means there is no overflow. Okay, so if overflow is happening, right? Let's say you did a calculator, right? We designed a calculator, and in the calculator we need to make sure there should be no overflow, right? So if overflow is happening, we need to detect it, right? And then give an error message, right? We can say overflow happened. Let's say preventing overflow. So there are basically two ways. One is we will call it sign extension. Do a sign extension before the operation. Okay, so basically in this case we are increasing the bit width. So if you are doing operation with 4 bits, if possible, if you have some resources, right, this is using some digital circuits, you can try to use one more bit. So instead of, let's say, 4 bits, you can use 5 bits, and then in this case you will not have an overflow because you are increasing the range. Or you can minimize your error and you can do a saturation. So this will not give you a correct result, but this will minimize the error. So the result is still not right, but at least the error is less. Okay, so this will give you a sign extension, will give you correct result. The saturation will not give you the correct result, but at least it will minimize the error. We will do some examples of these two methods. So let's say I need to add plus 5 and plus 3. So this is plus 5 and this is plus 3. So if I add this, I will get this number, and as you see, I added two positive number and I got negative number. So there's an overflow, right? So if I do sign extension, let's do sign extension. So instead of 4 bits, then I will use 5 bits. So before the operation, what will I do? So this is my 4 bits, and I do a one more bit addition here. Let's do it with a different color. So this is my sign extension, and this is my sign extension bit for the other. So this was 0, 1, 0, 1, and this was 0, 0, 1, 1. So the sign extension means I just add a sign bit here. So my sign bit is 0 here, right? So I will be adding another sign bit for each variable. So that's why it's called sign extension. So now if you do the addition, you will see, so this is 0, 0, 0, 1 and 0. Now my sign is, this is positive, so this number is plus 8, right? So no overflow, and our result is correct, right? So by using this sign extension method, I can avoid overflow, right? So that I make sure my range for my representation is big enough for all my operations, right? So in this case, since I have 5 bits, I can represent number from minus 16 to plus 15. So this is my range. So if this range is also not enough, then you need to add more bits, but to the left, right? So I will be adding the sign bits to the left, right? Let's do one more example. Okay, in this case, I will be adding minus 4 and minus 5, and the result should be minus 9. But since I will be using 4 bits, I cannot represent minus 9, because I can only go down to minus 8. So this will give me an overflow, right? So this is minus 4, so minus 8 plus 4. So this will give me minus 4, minus 8 and plus 5. This will give me, no, I should be having plus 3 here. So this will be giving me minus 5, right? So if I add this, I will get 1, 1, 1. 0, 1. So I discard this because I have only 4 bits. So this is plus 7, which is wrong, right? So I had overflow because I had 2 negative numbers, but the result is positive. So this is an overflow. So to correct this, I will be doing sign extension, right? So this is my number 1, 1, 0, 0, 1, 0, 1, 1. So I will be extending the sign. So my sign in this case is, in both of them is minus 1. So I will be adding 1 here. So now I have increased it to 5 bits, right? So now let's do the addition. We will have 1, 0, 1, 1, 1. And if I check what is this number, the short way is, so the weight here is minus 16. So this is plus 4, plus 2, plus 1. So this is minus 9, right? So the result is correct. So after sign extension, my result is correct. So this is how you do sign extension to prevent overflow. Basically what we are doing, we are extending the sign of our number. The second method was the saturation method, right? So in this case, we keep bit width the same. So we are not using more bits, but we will be saturated. And then let's do these examples, the same examples with the saturation. So in our example, 0, 1, 0, 1 and 0, 0, 1, 1. So we add this. So in this case, saturation work like this. So you look at the sign of your operators, they are positive, and the result is negative, you know overflow. So once you detect overflow, then you can do saturate to positive 7. So what happened? I added 2 positive numbers and I got a negative numbers. I know I had this circle, right? So I had plus 7 here and minus 8 here, right, in my circle. Since I went over this boundary, it gave me a negative number. So to correct this, since I cannot increase my bit size in this case, I am saying I added 2 numbers, 2 positive numbers. So the best I can do, I can make my result saturated to the most positive numbers, right? So I am adding plus 5 and plus 3, so I should get plus 8. I cannot represent it, but the best I can do is I can saturate the result to plus 7. So this is the best thing I can do. The best I can do with 4 bits, right? So what happened? This is the saturation result. So actual result should be plus 8, but the saturated result is plus 7. So the error is plus 1, right? So this is the error with saturation. So if I don't saturate, right? So the actual that I expect plus 8 with the overflow result. So what is the overflow result? So overflow give me minus 8, right? So what is the error in this case? The difference between these two is plus 16, right? So this is the error without saturation. So using saturation, I minimized my error to plus 1 from plus 16. So this is a much better result compared to the if I don't do any saturation, right? The error will be much higher. So let's do the same thing with the minus 4 and minus 5. So I am trying to add minus 4 and minus 5. I should get minus 9 in reality. But what is happening? So this is 1, 1, 1, 0, 0. This is minus 4, 1, 0, 1, 1. This is minus 5, right? When we add this, what we got? 0, 1, 1, 1. So we got plus 7. So this is without saturation, right? And I know I added two negative numbers and I got a positive number. So I know there's an overflow. So the best I can do, I can saturate it. In this case, when I do saturation, because I am adding two negative numbers, I need to saturate it to minus 8, right? So this is the best I can do, right? Because if you add two negative numbers, the result should be negative. And then the lowest number that I can represent in negative is minus 8. So now if you check the error, so I got minus 9 and then the saturation is minus 8. So the actual should be minus 9. So the error is minus 1, right? But in the other case, if I don't do saturation, the error is minus 16. So this is no saturation. So these are the errors in both cases. So what saturation does is it just minimizes our error. So in some applications, so as long as the error is less, it might be sufficient for you. So you can just tolerate these small errors, but you may not tolerate a big error. So saturation might be helpful in some cases.